All right, we're doing the Math 1030/1035 Exam 2 review that was created in summer 2023. Just a bunch of questions that are basically from the homework. And that's not what I wanted. Let's see, get the recording on Zoom as well. All right, so this exam will be for the statistics and the probability modules. And I'm just going to jump right into this review, and hopefully everything that I say is similar to what your teacher, if you're from a different class or if you're online from what the book says, is something similar and helps you out. Here we go. So match the name of the sampling method descriptions given. Situations: dividing the population by gender and choosing 30 people of each gender. So when you divide up the population first, you are stratifying, creating strata, and then you choose from that. So this one, A is E. Asking people on the street, very convenient. This is convenient sampling. Calling every 15th phone number on every 5th page of a certain phone book, that would be a systematic. That's when we ask computers to do work for us. Then we have to tell them instructions, and that's the type of instruction we would give them. Writing everyone's name on a playing card, shuffling the deck, choosing the top 20 cards, that is simple random. That's what we would like all of our sampling methods to be if we could get them. Everyone has an equal chance of being in the list. Whereas with the systematic, if you are the first through the 14th person, or any person on the first 4 pages, you will never be chosen. Therefore, it's not simple random. Finally, selecting a classroom number at random and then surveying all or doing a census of that classroom, that is a cluster. You choose a cluster in some way, and then you ask everyone in that cluster. These are very common sampling techniques. Okay, number 2. A study claims that the combination of vitamin C with vitamin E is more effective for preventing the flu than vitamin C alone. In the study, a group of researchers studied 1,132 subjects. The subjects were randomly assigned to out of 3 study groups, not quite sure what that is, but into 3 study groups. The first group of 310 subjects were instructed to take 600 milligrams daily of vitamin C. Second group, 408 subjects, 600 milligrams vitamin C and 200 international units of vitamin E. And the third group, size 404, some vitamin C and more vitamin E. The incidence of flu over a season was recorded. All subjects knew which treatment they were receiving. Okay, so first off, what is the control group? So there are 3 groups. There's C with E, and C with more E. The C with E and C with more E are the treatment groups, because we're studying if the vitamin E helps with in addition to vitamin C. And then the control group is just the vitamin C. So the control group, that is not what I wanted. There we go. The control group is just vitamin C alone, and there are 2 separate treatment groups. The study is not blind because all subjects knew which treatment they were receiving. Now, if the groups did not know which one, then it's at least blind. Going from blind to double blind, then the people giving the different pills to the different groups, if they also don't know what they're giving, then it's double blind. And not an experiment, would be just like an observation. You're just looking at like what's the most common colored car in your neighborhood. You're not doing any experiments. So an observational is more what you would be looking at for an experiment, not an experiment. So single blind, double blind, or not blind. If the people know what they're getting into, it's not blind. All right. Let's see if I can work this whole thing. There we go. Number 3. A team of researchers is testing the effectiveness of a new HPV vaccine. They randomly divide the subjects into 2 groups. Group 1 receives new vaccine. Group 2 receives the existing vaccine. The patients in the study do not know which group they are in. So the treatment group, when you are doing a new type of vaccine, you can't really do a placebo because that's unethical. You already have a treatment that works, the existing HPV, so that the existing or current level of care is the control group. So group 1 is the new, group 2 existing, the treatment group is group 1, the control group is group 2, the standard care. Blind, single, double, the patients don't know, but it doesn't say anything about the researchers. So we can't go to double blind, but we can for sure go to single blind. Which best describes this research? It is not placebo controlled because you can't give people a sugar pill instead of a vaccine. That's not safe. It is an experiment. It's specifically a controlled experiment because we do have a treatment group. So this one is a controlled experiment. All right, number 4. The city of Fredericksburg has 8,293 registered voters. There are 2 candidates for the city council in an upcoming election, Marfani and Rahman. The day before the election, a telephone poll of 350 randomly selected voters was conducted. So this would be the sample, whereas this is the population. Of the ones called and responded, 142 said they would vote for Marfani, 104 they would vote for Rahman, and 104 were undecided. So the population size is 8,293, whereas the sample size is the 350. And there's a lot of other questions that could come about here, and there are some other questions like number 6 coming up that have other information besides this. But as far as just which one's the population and the sample size, please note that the sample is always smaller or equal to the population, in general smaller. If the sample is the entire population, then it's not a sample really, you're doing a full census where you ask everyone. All right, number 5, we want to know what percentage of California will be voting for Mr. Lewis. 150 random numbers ask, are you planning to vote for Lewis? So it's like a yes or a no. Match the following descriptions with the appropriate key term. Now, population and parameter go together, whereas sample and statistic go together. And this is a nice way to remember it. The P, populations, and the S, sample statistic, kind of tie these together. So the population is the overall population, and the parameter is what you're studying in the population. The sample is the smaller group, and the statistic is what you're studying of the smaller group. So the population and the sample are similar as far as their groups of objects, and the parameter and statistic are similar because that's what you're studying about those objects. In this case, we are talking about people. So both the population and the sample are people, and the parameter and the statistic is proportion. The proportion of people that are going to vote for Mr. Lewis. Oh my goodness. Okay, so the proportion of the 50 random numbers who said they're voting, that would be the statistic. The responses of all voters, that would be the parameter. The proportion of all voters, hold on, the response, no, I'm wrong. The responses of all voters, that's the entire population. The proportion, what you're studying from the responses, is the parameter. And finally, the responses of all of the 50 random number, that's your sample. So the responses are the people that you're getting information from, and the proportion are how many of those said that they were going to vote for Mr. Lewis. All right. Next up. Oh, what's that there for? Get out of the way. Well, it's just there. Weird things with PDFs, and we'll get there. Here we go. All right, number 6. The city of Raleigh, sorry. I don't know why I said Raleigh, that's wrong. The city of Raleigh has 9,100 registered voters, 2 candidates. We have a telephone poll of 350 people. So this would be the population size. This would be the sample. And then we have a certain number from the sample saying that who they'd vote for. We want to work the sample statistic for the proportion. So this is a fraction of voters who surveyed said they would vote for Brown. So Brown, we have 170 said they'd vote for Brown out of the total of the people asked, which is the 350. And in general, you will want to simplify these fractions. You don't have a graphing calculator to use on a test. However, I'm only using the buttons that are equivalent to your scientific calculator, so you should be able to figure out in your calculator how to simplify fractions. Many of you will have a fraction button in this area of your calculator, and you can do second fraction button or just fraction button. You can type in 170 over 350 and hit enter, and it'll simplify for you. So we have 17 over 35. Of course, you could just reduce the zeros and get that as well, but however you manage it, in general, you will want to have a simplified fraction. Okay. Now, you want to be careful, because if you actually go to decimal form, you would then tempt yourself to round, like 0.49. And you'd lose a bunch of information if you did that. So let's say we did go to 0.49, and that's 49% of the 9,100 people. That would be a certain number. That's 49% of the 9,100 people. But we don't have 49%. Maybe it's 0.486. Maybe we round to 3 decimal places. Still, it's a different answer. Which answer is correct? Neither of them. What you want to do for applying the sample statistic to the overall population is don't round at all. If we do this one, we get a different answer still. This is the correct answer. The other ones are approximations because we approximated 17/35 to get them. You don't want to lose credit. You want to get the full precision. This is 4,420. There we go. That's question number 6. Number 7. Determine whether each observation below is qualitative or quantitative. Now in general, qualitative and quantitative. Quantitative is number and qualitative is like adjective. Red, blue, yes, no, etc. The height of a plant is 19 centimeters. If it takes measurement, then it's quantitative. A solution turns green. It's an adjective. Qualitative. A solution bubbles and fizzes. Adjective, adjective. Qualitative. The temperature decreases by 11 degrees. Now that's back to a measurement. So instead of number, maybe measurement's better. Quantitative. The ones that are harder to decipher would be like zip codes. A zip code, you don't measure to find the zip code. A zip code's actually an adjective of a location. Or jersey number, number 23, Michael Jordan. They didn't measure him in any way to determine the 23 was his number. It was more an adjective. It was a description of who he, it wasn't a description, it represented Michael Jordan. So jersey numbers and zip codes and social security numbers are not things that are measured. They're more qualitative information. Okay. Fill in the blanks. Now this is all still from gathering data. We're not describing data yet. When we get into like standard deviation, mean, median, mode, this is all still, let's see, it was quantity, collecting data. That's what it was. This is from the collecting data material. We'll still do the describing data. Fill in the blanks. The blank of a data set, which is sometimes called the average, is found by adding up and dividing. Okay. The middle number, the most common, the gap between. Most common, most and mode. It's a nice way to remember the one that's most common is the mode. Literally the middle number. In the middle number, if you have a road, the middle of that road is called the median. And then having to do a bunch of addition and division is mean. That's why people don't always like math, because they have to do a bunch of work. And then the gap between the largest and smallest number is not a measure of center, it's a measure of spread. This is the easiest measure of spread, the range. So the top 3 are all considered like average, even though they're not all average. The top one's the literal average definition, the mean. And the bottom one is a measure of deviation or spread. Okay. Next up, number 9. The table below shows the scores of a group of students on a 10-point quiz. Now this is a frequency table. One thing that is useful for you to be able to do is to go from a frequency table to a long list. For example, the test score 3 shows up once. A test score 4 shows up twice. So the test score of 5 shows up 2 times. 6 is 4 times. 7 is twice. 8 is once. There actually is no 9. And 10 shows up twice. Being able to go from a frequency table to the original data is very useful. It's not necessary, but it's useful. Being able to go from the original data to a frequency table is also something that's very useful and sometimes even on tests. All right, the mean, this is the mean one where you have to do all the work, add all these up and divide by how many there are. Now, if you add up the frequencies, 1 plus 2 plus 2 plus 4 plus 2 plus 1 plus 0 plus 2, that will be the total number of scores. So making sure I don't make any mistakes on review day, and also to mimic what I would be doing on a test, which is basically never putting my calculator down, just leave it in my non-dominant hand. 14. So the mean would be divided by 14. Now, since we have the whole list, we could go in and just do 3 plus 4 plus 4 plus 5 plus dot 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 plus 10 plus to add them all up and divide by 14. By being able to write the frequency table as the original data, we can now see them all, add them all up, and see what we get. But we can also, so for example, these 4 sixes would add up to 24. We can get that by multiplying the test score and the frequency as well. So if we were to just multiply all these, 3, 8, 10, 24, 14, 8, 0, and 20, and add those up, that'll be the numerator. $87. When you go to divide, let me first do a quick fraction. It does not reduce. If we were to do the division, we would then ask ourselves, where do we round? Meaning, we're asking ourselves, how bad do we want our answer? If we call this 6, that's bad. 6.2, not as bad. 6.21, better. 87 over 14, perfect. Don't round unless it asks for it. That's the mean. It's approximately 6.2 if requested. In general, the mean, standard deviation, etc., 1 decimal place more than the original data. The original data had no decimals, and so the mean, I would go with 1 decimal. The median, there's 2 ways to do the median. You can do the percentile method, what the heck, which is a really important way to do it because this is how you get the 5-number summary. 0.5, there are 14. Half of 14 is 7. If it's a whole number, you do the mean of the 7th, I don't know where that 17th came from, 7th and 8th. This would be the percentile method. The percentile method is what is required on the exam for the 5-number summary, so you want to know it. You can use it for the mean. Between the 7th and the 8th, the 7th one in this list, here's where it's nice to have them listed up. 1, 2, 3, 4, 5, 6, 7th, and the 8th. We want to mean 6 and 6. That's easy. 6 plus 6 over 2 is 6. Could we find that with the frequency distribution, the 7th and the 8th? 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all right in there. They're all 6s. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The 6th, 7th, and 8th are in this category. They're all 6s, so the median would be 6. Now, if you have them listed out, if there's an even number, there's a gap in the middle, right here. That's the actual median. There are 1, 2, 3, 4, 5, 6, 7 on the left, 7 on the right. When there's a gap in the middle, that's where you mean the middle two. What's halfway between 6 and 6? 6. Multiple ways to get the median. I hope that makes sense. Number 10. Highway mileage for a sample of 5 different models of a car company can be found below. 1, 2, 3, 4, 5, 6. There are 6 values. On this one, I don't know if there's a standard deviation question on here. It has been requested in the chat to do one, so I will do a standard deviation of this if there isn't one. So I might come back to this question. But for mean, median, mode, range, it's pretty straightforward. The mean, parenthesis, 21 plus 23 plus 26 plus 28 plus 28 plus 30, parenthesis, divide by, how many are there? There are 6. 26. So to get full credit, you do need to show your work on the test. I don't care if they give you scratch paper and then forget to tell you scratch paper is going to be shredded, or remember to tell you. Either way, you want full credit. Show work on the test. You would write this down. And you have full credit for the mean. The median. There's a gap right in the middle. Halfway between 26 and 28. You could just see it's 27, but you could also do the mean of those two and calculate it. The mode is the most common. There's two 28s. 28's the most common. The range is the largest number minus the smallest number. These are your basic mean, median, mode, and range of the original data. So let me just do a quick check. I do not see standard deviation. I see lots of fun stuff coming up, but not standard deviation. All right, so step 1, find the mean, which we've already done for this problem. It was 26. Step 2, you take the original data. Let's see, how do I want to do this? And subtract the mean. So however many numbers you have originally, we're still working with that many numbers in the standard deviation. Step 3, you square. So negative 5 squared is positive 25. Negative 3 squared is positive 9. 0 squared is 0. 2 squared is 4. 2 squared is 4. And 4 squared is 16. The point of this step is to make your numbers positive. Now you can see they also got bigger in general. We will have a square root step as our final step to make them back down to the similar size as the original numbers. Okay, so step 1, you find the mean of the original data. Step 2, you subtract the mean from the original data. If the original number is smaller than the mean, the subtraction will be negative. If the original number is larger than the mean, it'll be positive, and you might even have the original number equal to the mean. The difference will be 0. The next is you square it. So far there should be no big decimals. If you do get a decimal for the mean, you might have a decimal here. When you square one decimal, you end up with like 2 decimals. So you might be running, 2, 3 decimal places, but you shouldn't have to round anywhere yet. The final step, when you square root it, you might end up rounding. And the standard deviation general rule is the last step. You round to 1 decimal place more than the original data. So our final answer should have 1 decimal place since we have none to begin with. Okay, so again, this shouldn't have any major rounding yet. The fourth step, you add them up. All of these numbers are now going to be combined. Now this is like a mean, but it's not a mean, because although there are 1, 2, 3, 4, 5, 6 numbers, we always divide by 1 less than how many you have. And this makes the sample standard deviation, the deviation of a sample, more closely resemble the population's standard deviation. So the sampling makes the standard deviation too small. So if you divide by a little bit smaller number, then the value is a little bit larger than it would have been, and it makes it a better model for reality. So this whole process, standard deviation, if you want to do the standard deviation for every person in the United States, go right and do it. You'll get a number. But who wants to do that? This is a hard process. Instead, you sample 1,000 people, do the standard deviation of that, and if you don't do this divide by 1 less, your answer will be too small compared to the real standard deviation of the population. So this dividing by 1 less, always 1 less. If you have 10 to begin with, 10 numbers, here this step would be a divide by 9. It makes it a better match. Okay, so let's work that out. Parenthesis, 25 plus 9 plus 10 plus 4 plus 4 plus 16 divided by 2, 34. And finally, the last step, square root. And here we round to 1 decimal place. 5.8. This would be the process of the standard deviation. So you start with, in this case, 6 numbers. You find the mean. Then you subtract the mean from the 6 numbers. You still have 6 numbers. Then you square them. Now you have 6 positive or non-negative numbers. Then you quasi-mean them. You get to 1 number. Did I divide by 2 on the calculator? I divided by 2. What the heck am I doing? This is wrong. Give me a moment. Divide by 5. Thank you for those of you that noticed that. I don't know why I had a divide by 2 on my calculator when I wrote a divide by 5. That's just my mistake. I'm so glad you guys caught it. So dividing by 5, 13.6, and then square rooting 13.6. 3.7. All right. So we go from 6 numbers, do the mean, still 6 numbers, still 6 numbers. The quasi-mean gets us to a single number, then square root that. Without the square root, this is called the variance. If you take statistics, the variance is something that's useful as well. But square rooting that, this is the standard deviation. The bigger the standard deviation is, the more spread out the data is, the wider it is from the mean. If you get a standard deviation of 0, then all the numbers would be identical. They'd all be 26s. And then there's no deviation at all. If this is 21 and 26 and like 80, the 80 will make the spread much larger, and you would get a bigger number. The standard deviation is always 0 or positive. You'd never get a negative standard deviation. All right. The standard deviation can be used to determine how spread out the data is. So number 11. 2 classes were given identical quizzes. Class A had a mean score of 7.7. And a standard deviation of 0.2. Class B had a mean score of 8.6 and a standard deviation of 1. So on a number line, here's 5, here's 10, here's 7, 8, 9, 10, 7.7. The standard deviation of 0.2 means that most of the scores were very close to 7.7. 8.6, the standard deviation of 1 means that the spread was wider around that 8.6. There was more variation. So, which class scored up better on average? Well, the red line is higher. That's the B. Class B had a higher average. Which class had a more consistent set of scores? That would be the blue scores. They're more close to the center. So that would be Class A. Now, if you were in class, which class would you rather have? Would you rather be in a class where it's a little bit lower average but everyone's all bunched up there, or a higher average where there's a chance that you did worse? So there's probably some people in this red class that did worse than people in the blue class, but they also did way better. I don't know, it depends. Depends on the situation. If I were hiring, I would probably hire the blue group first because I'd know they were all basically the same candidate. They had the same skill set. Whereas if I hire the red group, I might get a way good candidate, but I might get a really poor candidate. So it depends. Depends on the situation whether you'd rather have a higher mean or a higher or a lower standard deviation. Okay, that is question 11. We're on to question number 12. We're getting there. Question number 12. Here's a bunch of data. Happily, they're in order. That's sometimes the hardest part of statistics, is putting all the data in order. It's where it's nice to have a tool like Excel that does it automatically. Complete the frequency distribution for the data. How many are between 10 and 19? 1, 2. How many are between 20 and 29? 1, 2. Between 30 and 39? 1, 2. Okay, so far we have a flat distribution. Between 40 and 49? 1, 2, 3, 4, 5. Between 50 and 59? 1, 2, 3, 4, 5. Between 60 and 69? 1, 2, 3, 4, 5, 6, 7, 8. Between 70 and 79? 1, 2, 3, 4, 5, 6. That's what it takes to create a frequency distribution. Now, if it had relative frequency, then we'd have to take the 2 and divide by how many there are, 30, and then determine where do we want to round that. There's rounding involved. 0.067. So you would have to do the divide by 30 and round, or you could go to a percentage and call that 6.7%. But those are all approximations. The frequency table itself is exact. Okay. Now if it's the frequency table histogram, then you'll notice on the left whole numbers. If it's the relative frequency table, you'll notice on the left, decimals. And on the Magnets and Paint project, they were decimals. Here, this is just frequency. So, number 10. 10 through 19. Frequency 2. So the bar over 10 is height 2. 20 through 29, same thing, height 2. 30 through 39, height 2. 40 through 49, height 5. 50 to 59, height 5. 60 to 69, height 8. 70 through 79, height 6. And 80 through 89, there isn't any. There shouldn't be that gap right there. There we go. This is the histogram represented by this frequency table. If you're creating your own histogram and you want people to be able to interpret your data, some people put the heights right above. It makes it a little bit easier to interpret. You don't have to, assuming it's correct. But if you did like my line, it's crazy, like should have used a ruler line, then if I label it, now it might not be precise, but at least it's accurate. Okay, from original data to a frequency table or relative frequency table to a histogram. Very useful skill. Number 13. Here we have a chart. It's a bar chart. Now the histogram is a type of bar chart. I messed something up when I moved it. Anyway, the histogram is for quantitative data, but here we have categories. This is just a bar chart. not a histogram. This represents 40 students. And these are all percentages. I'm just reading the information to figure out what is going on here. So 20, 30, 30, and 20. That's 100% of the students are represented. All right, that makes sense. What number of students earned a A? Oh my goodness, English people? An A on their paper, 20%, but that's not a number. 20% of the students we have to work out. 8. Eight students. What number of students earned a C or better? A C or better, we have 30%, 30%, and 20%. That's 80%. That means 0.8 times 40, 32. Again, all this stuff on a test, I would not be messing around with my brain. I'd be doing all that work on a calculator to make sure it's correct. All right, number 14. Here we have a pie chart, kind of a fuzzy pie chart. Kara categorized her spending for this month into 4 categories. The amount she spent in each category pictured here. What percent of her total spending did she spend on rent? Well, so her total spending is something we need to work out. The total spending is all of the categories added together. Again, don't mess around with your brain. Your brain has enough to worry about on test day without making it do addition. $1,500. What percent of her total is on rent? So here we take the rent value and divide by the total value and times by 100%. And what happens, the units dollar sign reduce. The only unit that'll be left over is the percentage sign. Calculator did everything. We didn't have to worry about much of anything. 27.8%. That's the percentage she spent on rent. Between 25 and 35 is really a good goal to have percent on your housing. I'm assuming rent also includes all the stuff about rent, like mortgage insurance renter insurance and bills for utilities. Hopefully she took all that into account. Maybe that's an other. Anyway, here we go. Number 15. Based on the histogram on the left, what is the class width? The class width can be best found by looking at the bottom numbers. Doesn't matter where you do this, because histograms have the same class width. That's one of the definitions, one of the requirements to be a histogram, is the class width are all the same. What is the sample size? Now this bar right here represents 3 people. I assume they're people. I don't know what they are, but there are 3 of them. This is 10 of them. This is 5. This is 7. So I'm just looking over to see the height. 7, 4, and 9. The total sample size is found by adding up the total frequencies. 38. Okay. Number 16. Find the 5-number summary. Now the 5-number summary, 2 of them are trivial. Don't miss these. The minimum, the smallest number in there, 4. The maximum, the largest number in there, 57. If these numbers aren't in some type of order, put them in order. You could even reorder these linearly. So it's like 4, 6, 7, 14, 21, 34, 43, etc. If you wanted to, if that helps. Sometimes these are larger tables and it's best if you not spend time rewriting or not take a chance of transcription errors. Okay. So Q1 is the 25th percentile. The median is the 50th percentile. Q3 is the 75th percentile. So for Q1, we work out 0.25 times the total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 total values in this data set. So let me just do all these. Q2, which is the median, 0.5 times 10 gives us 5. Q3, 0.75 times 10 gives us 7.5. Now the rule that we use, this 2.5 is basically somewhere around the 2.5th term. What? Here's the terms. This is the first. I didn't want that one. First, second, third, fourth. These are locators. Which term? 2.5th term is somewhere around here. Do they mean the second? Do they mean the third? Do they mean the mean of them? What do they mean? So the rule of these percentile locators is if it's a decimal, go up to the next one. If it's a whole number, mean with the next one. So for the 2.5th, that tells us to go to the third. The 7.5 tells us to go to the 8th. So if it's a decimal, we go to the next higher whole number. The third one, 1, 2, 3. That's Q1, 7. It told us to go to the third one after we interpreted it. For Q3, it told us to go to the 8th one. 1, 2, 3, 4, 5, 6, 7, 8. There it is. The 8th one is 53. Now, if you get a whole number out of the locator method, then you do the mean of the 5th and the 6th. Actually, I don't want to divide there. Mean the 5th and the 6th. So that is when you add them up, divide by 2. The 5th one is 21 and the 6th one is 34. Back to our calculator. 55 divided by 2. 27.5. This is how you find the 5-number summary with the locator / percentile method that is taught in this book, in this class. There are other methods. The 5-number summary, sadly, is not a unique answer. Depends on which book you learn from, but we're very specific about using the locator percentile method on the test and on the homework, and this is how you do it. Okay, so you always do the 0.25, 0.5, 0.75 times how many there are, 10 total here. And then if it's a decimal, go to the next one, and that location in the data set is that quartile. Nice. Number 17, next up. 17 is a box plot. The box plot is a visual of the 5-number summary. 1, 2, 3, 4, 5. Those are the numbers: 12, 14, 15, 17, and 18. That's the 5-number summary. I hope for your sake that you have a problem like that on the test, because you get to move on. You get more time to go and work the rest of the test out. That's crazy how easy that is. Just a quick look at the time. We're about an hour into this, so it looks like I might need until until 4 o'clock to finish the probability. I will make this recording available to my classes, and if you're from another class, then hopefully they'll be able to get this recording up and available as well. Okay. Number 18. The box plot, the dual box plots shown below, salaries for construction workers and teachers. If a person is making the median salary for the construction worker, where are they? The median is the middle. They'd be making $45,000. They are making more than what percent of teachers? So the median, we have 25%, 25%, 25%, and this is 25%. The 5-number summary literally breaks the data up into quarters. So the median construction worker, 45,000, is above 3 of these quarters of teachers. That's 75%. So this is 25% of construction workers. This is 25% of construction workers. Here, 25% of the construction workers are all bunched together between 45 and 47,000. And then 25% of the construction workers are there. So there's an equal number within each quartile. It just gives you an idea of how spread out those people are as far as their salary. If a teacher is making a salary that is exactly the first quartile, they're making $30K or $30,000, depending on which way you want to. You could even write 30,000 in English. Just make sure you don't write 30, because that would not be correct. The teacher's making exactly one first quartile, 30,000. That means they're making more than 25% of the other teachers, but they're making less than 75% of the other teachers. All right. 5-number summary. Box plots. Number 9. Which of the following does not, 19, does not reveal the variation or spread of the data? This is spread. This is spread. This is average or center. This is spread. Which one does not reveal the variation or spread? The median. If you just know what's in the middle, you have no idea of how wide the road is. If you're standing in the middle and you're not looking left and right, that would be the range, or the 5-number summary, or the standard deviation gives you an idea. If you're just standing in the center, you don't know how far each side is. Like if you're in the middle of the ocean, do you know how wide the ocean is? Not at all. All right, number 19. I believe we are now into probability, right at 3. Okay, good. Probability time. Number 20. A bag of M&Ms has 4 red, 5 green, 7 blue, and 2 yellow M&Ms. What is the probability of randomly picking a yellow? Well, the probability is how many successes of finding a yellow over how many total events can happen. That's 9 and 9 is 18. And instructions, reduce your fractions. The probability of picking a yellow is 1/9. Theoretically, every 9 times you choose an M&M, once will be a yellow. In actuality, you might get yellow first time. You might get 2 yellows in a row. But theoretically, 1 out of every 9 should be yellow. Blue or green. Now, blue or is addition with probability. 7 blue or 5 green. Doing the same way, how many blue? 7 out of 18. How many green? 5 out of 18. Or you add them up. 7 and 5 is 12. And then you reduce. 6 goes into 12 twice, and then 18 3 times. But none of that's going to be what I do on a test. I'm going to be wearing out my calculator. You've got to know your buttons. Nice. Probability of an orange. Well, there's 0 oranges out of 18. That's an impossibility. When you get probability 0, it's an impossibility. When you get probability 1, it's a certainty. A red, and without replacing the red, a blue. Now this is an and. And is multiplication. So getting a red one, 4 out of 18, times, if you eat the red one, now there's 17 in there. Now there's still 7 blues. Now this could have been a red and without replacing a red, in which case we'd have 4 over 18 times 3 over 17, because there's only 3 reds left. But without replacement, the sample size decreases. 18 down to 17, you do it again, down to 16, etc. The numerator might or might not decrease, depending on if you're picking the same thing again. Now if it said with replacement, then it would be another 4 out of 18, because there's still 4 reds and still 18 total. So you got to watch out whether it says with or without replacement. The only thing I could reduce here but I still have to do all the multiplication, so I would probably just take the safe approach. 14 out of 153. All right, number 21. A card is drawn randomly from a standard 52 card deck. Find the probability of the given event. The card drawn is a 7. Well, there's how many 7s? There's 4 7s out of 52. And you can reduce that to 1 over 13. The card drawn is a face card, or pluses, pluses. There's 4 jacks, there's 4 queens, there's 4 kings. That would reduce to 3 out of 13. The card drawn is not a face card. Well, since we just did face card, we can do the probability of not, which is 1 minus the probability of is. That would be one way. Or, how many are not face cards? There are a total of 12 face cards. So there's 52, 12, 52, 40. There's total 40 that are not face cards. Reduces to the same thing. So ace through 10. 10 of them. 10 hearts, 10 spades, 10 clubs, 10 diamonds. There's 40 total that are not face cards. So you have a choice there. The not probability rule is 1 minus. Is a nice rule to know. But that's that. Number 22. Student grades in 2 courses are summarized below. If one student was chosen at random, find the probability that the student took COM 1080. COM 1080, there is a total of 22 COM 1080s out of a grand total of 63 in the sample. That doesn't reduce. You could also say there are 7 A student COM 1080s, there's 9 B students, and 6 C students. You could do it that way as well. In other words, you could individually see all the COM students over the total, or you can utilize the fact that they already found a total for you. If one student was chosen at random, find the probability the student did not get a B. These are all the people that did not get a B. Add them up, divide by the total. These students did not get a B. You can utilize the sums if you'd like. 38 out of 63. You can do that by adding up the not B's or equals, or individually adding up the not B's over the total. Or you can do 1 minus the B's, because again, the not is the 1 minus rule. How many B's were there? 25 out of 63, which again reduces to 38 out of 63. Multiple approaches. Now, does 38 out of 63 reduce? Brain says, calculator says no. Great. Number 23. Making progress. We're getting there. Number 23. The gender and breed of dogs who visited the veterinarian's office this week are summarized below. If one dog is chosen at random, find the following probabilities. Round each to the nearest hundredth. 2 decimal places. Okay. There are 2 approaches to these problems. There's the knowing the and or rules, and there's just directly looking for what you need. For example, the rule, probability of female, times, and is times, probability of mixed breed, given female. I really don't like that one because the and probability has a conditional probability into it, so I don't usually do it that way. I much prefer doing it this way. Find the female mixed breeds. There they are. Total. That's that. Now, probability of female. How many females are there? 24 out of 65. Probability of mixed breed, given that they're female. Given that they're female is 24. How many mixed breeds are there? 7. I mean, it works out. It's just more awkward to do it with this rule. I know the rule well, and you'll need to know the rule well for the incidence rate problems, which are some of the harder problems in this module. But it does work. Male or terrier. Now, or is addition. So we could do this with probability of male plus probability of terrier. But then there's also minus the probability of male and terrier. That's the rule. The probability being male, there are 41 out of 65. 41 male, 65 total. Probability of terrier is 24 out of 65. And minus the probability of the male terriers, the 10 out of 65. That's 41. I think it's 55 out of 65, which reduces 11 out of 13. But that's something, again, that I wouldn't mess around with my brain on test day. Know your tools. Now the other thing you could do is just circle, this time I'll highlight, male or terrier. Those are the males. Or terrier, we can include these 14 female terriers. And that also reduces to 11 over 13. So you can either use your probability rules or just directly look for what you need. Now the problem with just doing the totals, that's 41, that's 24. You double count these. So if you do 41 plus 24, male terrier, you've double counted the 10. That's why we have to subtract that double counting in the rule. All right, hope that makes sense. Number 24. A 6-sided die is rolled and then a card is chosen. What is the probability of showing a 5 on the die and? Now, and multiplication. A 5 on the die. One of those numbers is a 5. There are 6 total numbers because they told us it was a 6-sided die. Times a diamond. There are 13 diamonds out of the 52 cards. Some of you might choose there's 1 diamond suit out of the 4 suits. That's also correct because this reduces to 1/4. Either way, it all multiplies to be 1 over 24. That's that. Number 25 is a conditional probability. If one student is chosen at random, find the probability that the student was a STEM given, so this word given, conditional probability. It might be written probability of STEM, vertical line is given, they got a C. Now, the given part basically tells you what population that you're in. Given you got a C means that you are only in that, in this case, column. Sometimes the given is a row, sometimes it's a column. If it was given that they're non-stem, that would have been a row. This one's given that they've got a C. That column is the only set of numbers you look at. Now from that column, how many are stem? 11. How many are total? 20. So the given, the second part of the conditional probability, tells you which row or column you're in. Don't look at any other numbers besides that are in there. Now that we've reviewed that, I can go back to number 23. Mixed breed given female. If I highlight the female, now you can see the mixed breed were 7 and the total were 24. That's where that number came from. Knowing the AND rule. The AND rule is really a pain, especially when you have a table like this and you can just see the 7 that are female and mixed breed. But anyway, that's where I got that from. Now that we have that, undo. There we go. Conditional probability. All right, number 26. These questions are where it starts to get long. Okay. Now there are two basic ways that they give you this question. Excuse me. One is where they have this like 1 in every 200 people, but they might also say 0.05%, not 0.05, 5% or 3% or something. If they say 3%, I go with a sample size total. I usually work with 100,000. Because then the percents all work nicely in whole numbers and there's no decimals in my table. But I'm just creating a simulation of a population. But if it says 1 in every whatever, then I just add a couple zeros to that. That's how I generate this number on the bottom right. If you don't have a table already filled out, it's up to you to create one. And then in the bottom right, you need the grand total of your simulated population. So if it's a percentage, I go with 100,000. If it's a 1 in every however many, I add enough zeros to make that into a 100,000 multiple. Here we go. Let's start off with this piece of information. A test positive 85% of the time if the person has the virus. So that is a true positive test if they have the virus. 10%. So this is 10%. A test is negative. Oh, wait, a test is positive 10% of the time if it does not have the virus. I said 85. Oh my goodness. I caught my mistake. Hopefully you guys were spotting what I was doing. True positive, 85% of them. False positive, they got a positive test, but they were not infected 10% of the time. Okay. Now it's time to start filling some numbers in. A certain virus infects 1 out of every 200. So 1 in 200, if I add some zeros, 1,000 in our population of 200,000. 1,000 are infected. That's 1 out of every 200. The rest of them are not infected. One 99000. Now we have a percentage in the infected column. So if we were to work out 85% of the 1,000 people that are infected, I get 850. So in other words, out of the 1,000 people that have the virus, because it's only 85% of the time positive for those people, 850 people are getting a positive test. Applying the percent and the total there, 10% just wipes out a 0. That would be 19900. Of these people that are not infected, 10% of the time we get a positive test anyway. 19,900 people are going to get a positive test even though they're not infected. That sucks to be them, because now they're, actually that's not so bad for them unless it's a lie detector test and they go to prison. So it depends on the test, but in this case they're just going to be extra careful, or maybe they're going to take a whole bunch of medications that they didn't need. Hopefully they don't take antibiotics because it doesn't help on viruses, but all that good stuff. So we can now fill out the rest of these columns. For example, those add up to the grand total for the positive tests. $20750. These two have to add up to 1,000. So we can do that with subtractions. 1,000 minus the 850, 150. And similarly, the 199,000 people minus the people that got the false positive result, most of them got a true negative result, 179,100. Okay, and then we can add those up to get the grand total there. $179,250. Okay, now we're ready. Finally, we got this thing filled out. That's the hardest part of this process. Now we're ready to do the follow-up questions. Pick a different color, green. Find the probability that a person has the virus given, here it goes, given that they have a positive test result. So the thing after the given they have a positive test result, puts us in the category, in this case a column, that's of interest. Of those people, find the probability that the person has the virus. How many people had the virus out of those? 850 people. How many people tested positive? 20,750. Round to the nearest tenth of a percent. be very careful with this. Go to the percent, then round. Don't round and then percent. So let me just times by 100%. Write that in right away. 850 divided by 20750 times 100. 4.096. That's what we round. Tenth of a percent, 4.1%. Okay, so if you got a positive test result, there's only a 4% chance that you have the virus. That's crazy. But it's because of how many false positives there were. There's so many people that were not infected that we got a bunch of people that still got a positive test result. Do not include the percent sign. The reason for that is not applicable for your test, most likely, but if the answer blank already has a percent sign, then you don't need to include a percent sign. So you have to watch out for whether the answer on the test has a percent already there. If it does and you put 4.1% right here, I am not going to take points off. The computer homework does say it's wrong, but that's why that instruction is still there. That's basically, we're pulling these questions from the test, for the test from your homework. And that's the kind of questioning that you see there. Now find the probability. This is a different one, so let's go with blue. The person does not have the virus, given that they test negative. Negative test is, again, a column. We're only looking there. Given that you test negative, the grand total, that many people, find the probability a person does not have the virus. Most of these people do not have the virus. This is going to be almost everybody. Times 100%. Get to percentage first, then round. $99.9 when we round to one decimal place. So basically, if you get a negative test result, chances are very high you don't have it. But if you get a positive test result, chances are very high that you don't have it. That's sad. The way around this problem in society is multiple tests. So when Lance Armstrong was found doping, they sent his blood to multiple different laboratories and they all came back positive. That's how they knew that it was actually that he was doping. If you are wondering if you're pregnant and you go to the dollar store to get the super cheap pregnancy tests, their errors are higher, but if you get 10 of them, chances are likely that if one of them's wrong, the other 9 are right, and you'll get a better idea of whether it's actually a true positive or not. So multiple tests are important. Lie detector tests are not admissible because they're too easy to fake, plus the test itself has errors in it. Okay. That is the incidence rate type of problems where you have to create your own table. It's what takes these problems so long. After that, the given probability, conditional probabilities are the easy parts. I keep moving this and it moves right back down. I do not understand. There we go. Number 27. We're looking for expected values. You're given the formula. It's like amount times percent. No, what is it? Trying to remember the exact formula you're given. The value times the probability plus the value times the probability, etc. All right, so here we go. I do these slightly different than a lot of the books, but I do these in the best way I know how. Basically, if we're the company and someone buys an insurance policy, our expected value will be we make $180. How often? 100% of the time. 100% of the time, we make $180. Put that in the bank. Now, every so often, we have to pay out, so it's negative to us, the insurance policy. How often? 3.3%. And calculator work. By the way, on a calculator, I would probably be doing this letting the calculator do the divide by 100 to convert that percent into a decimal. 173.07. I think it's a lot easier to have the income be guaranteed. The book's approach to this, which is the way you might have practiced, so I'll make sure to show you, is that you get $180, not all the time, 96.7% of the time, and the rest of the time, you pay the $2,100, however, you use the $180 that they gave you to offset the charge. I just think that's a lot more complicated than it needs to be. Given how easy it was the first way, notice that it's still the same final result. What did I do wrong? It better be the same result. That looks right. Let me redo the first one. Through 3, 2100. Oh, no, that time I didn't do a times. Sorry. I'm being sloppy. I don't know where I got this 173. I must have just fat fingered it. Oh, thank you. Yep, someone caught it. 110.7. Same answer. Whether you, as a business, you just pocket the $180 and every so often pay out the entire insurance claim, or you pocket the $180 most of the time and use the 180 to offset the cost to the business the rest of the time, it's same answer. I just think this times 1 is a lot faster and easier. The customer's expected value, is the exact opposite as the company's expected value. You don't have to redo this process at all. With expected value, there's to one party or to the other party, company or customer, winner or loser, casino or player. There's always two people involved, and the expected values are always just the opposite of each other. Okay. There we go, number 28. Expected value. Okay, so to me, I'm going to play this raffle, and I guarantee you I'm going to lose that $4. I assume that $4 is gone. Now I might win $80 if I happen to get the one winning ticket out of the 270 that were sold. Do I get my money back? No. Sometimes they say you also get the cost of the ticket back, in which case you're actually winning $81. No, sorry, $84. In this case, you don't get the cost of the ticket back, so it's just 80. So it's minus 4, 100% of the time, plus 80, only 1 out of 270 of the time. Minus 370. I always wonder where, I think it's $sign and then the minus, or minus and the $sign up there. Either way, I expect to lose $3.70 every time I play this raffle. Honestly, I expect to lose all of it. The expected value, if I buy 12 raffle tickets, I expect to lose $3.70 every time I play. So let me see if that's the same if I round to the nearest dollar. Yeah. Oh no, there's actually pennies off. So you do round money. So even though it's minus 3.70370, it's just 370. So go with the 370 when you then buy 12 raffle tickets. $44.40. I expect to lose a bunch of money. Okay. Just give me one moment. I gotta let my cat out. And I'm back. Number 29. An experienced teacher writes an exam so that on average 5% of the students will earn an A. If she has 50 students in her class and their performance is independent, what is the probability that at least one student gets an A? All right. So 5% gets an A. That means 95% don't get an A. %95 to the 50th power, 50 students in a row don't get an A. One minus that, at least 1 in 50 do get an A, which is what we're looking for. So this is how you can build the at least one rule. It's 1 minus, so at least one does, 1 minus they don't, to however many students are involved. So 5% get an A. 95% don't get an A. 95 to the 50th power, because they're independent, you can just multiply 50 times and therefore do an exponent instead. 90.95 to the 50. 50 students in a row don't get an A. If at least one gets an A, then you're in the complement of none of them do. 1 minus that, at least one gets an A. (92.3%) probability decimal, just a decimal, not a percentage, 3 decimal places, 0.923. There we go. I think that finishes the questions in the review. And I did have a let's see, there's one question. 210. I want to make sure I didn't make a mistake. And we fixed that mistake. So, oh my goodness. Too many things going on. My computer's starting to lag. There was a question similar to question number 18. Let me find question number 18. Okay, and give me one more moment. All right, so the question is about number 18, just to clarify it again. With these box plots, what's really important to know about these box plots is the fact that in between the minimum and Q1 is 25% of the data. Between Q1 and the median is 25% of the data. Between the median and Q3, 25% of the data. And Q3 and max, 25% of the data. So if you were right here, Q3, you are making more than 75% of that population. If you're in the median, you're making more than 50% of the population, but you're making less than 50% of the population. So in this case, we can see that half of the people are really bunched up between 45 and 48,000. For whatever reason, there seems to be an upper limit on this construction worker position. You start way low, there's a lot of people, 25% of the people are between 30 and 40,000, but then 25% of the people are between 40 and 43,000. They're much more bunched up. I don't know why, where they got the data from. When you're comparing two different box plots, the median, I can see that the average median construction worker makes more than the average teacher. In fact, the average teacher only makes 25%, makes more than 25% of the construction workers. Whereas the average construction worker makes more than 75% of the teachers. The minimum construction worker makes more than 25% of the teachers. So if you happen to have lines that match up, this is really nice. On the Q1, first quartile construction worker makes more than half of the teachers. So in this question, a person is making the median salary for a construction worker, they're right here, compared to the teachers, they're making more than 25, 50, 75% of the teachers. A teacher is making a salary exactly the first quartile, they're making less than 100% of the construction workers. It's kind of sad, but they're making $30,000. Hopefully that helps. A little more clarification for these box plots. It's 3:47. I was planning on going to 3:30. Hopefully you guys all got what you came for and you feel a little more prepared for your exam coming up. I wish you the best of luck. I hope that your exam is a nice calm experience, or that you have a way to calm yourself down during the experience so that you can show what you know. Thank you so much, and I hope you have a wonderful test experience.